One of the biggest problems that we have in space travel is the lack of gravity between a person and another object, specifically the Earth. The gravity that the Earth holds us down with is what makes us walk the way we do when we have to lift things, but it also keeps our muscles in check. Being out in space, we don't have the same muscular exertion that we do on Earth. So one of the biggest problems is creating that environment. One of the ways that's been proposed to create artificial gravity in space is to have a large cylindrical tube-shaped spacecraft that spins, creating centrifugal force, creating acceleration towards the outside of the wall, and basically mimicking gravity out in space. So in this situation, we have exactly that. An astronaut on a rotating space station with an inside diameter of 3 kilometers. Yes, that is extremely wide, but we'll see as we do the math that width is important. Question A, determine the speed you need to have if your apparent weight is to be equal in magnitude to your earthbound weight. What affects our earthbound weight is the acceleration due to gravity on Earth, which means that the acceleration of this space station must be 9.8 meters per second squared. Since this has a diameter of 3 kilometers, the radius of the space station is 1.5 kilometers. Now we do need to convert this into meters to use it in a calculation. So 1,500 meters. The speed of the space station is what we're trying to find. And we can look back to the rotational kinematics equations from Unit 1. There is one that works perfectly here, is that AC equals V squared over R. Substituting in, AC is 9.8. V we don't know. And R is 1,500. It should be V squared, sorry. Cross multiplying will give us that V squared equals 14,700. Taking the square root, going to 2 sig figs, we get V of 120 meters per second. Now this may seem excessively fast. 120 meters per second is well over 400 kilometers per hour. But as we can see in B, this actually isn't as fast as you might think. Because B, we're being asked for the frequency in hertz and revolutions per minute. This is really what tells how fast the station is turning. Yes, you would have to go 120 meters per second, but when you think about it on a space station that has a 3 kilometer diameter, that may or may not be very fast rotation. This is what we're going to find out. So in question B, we need the frequency. Looking back to that same set of equations, we do have an equation with frequency. AC equals 4 pi squared RF squared. Substituting what we know, we already know AC is 9.8. 4 pi squared R is 1,500. And F is what we don't know. On the right side, we can multiply 4 times pi squared times 1,500, gives us 93,018 F squared. Divide both sides by 93,018. we get that F squared is 0.000105355 square root both sides. For the final answer, we need 2 sig figs, and we get f of 0.010 and frequency measured in hertz, meaning 0.01 revolutions per second. Converting this to revolutions per minute, take our frequency, multiplied by 60, because there's 60 seconds in 1 minute. Again, 2 sig figs, 0.60 RPMs. Now, while this is an excessively large space station, it doesn't even need to rotate a full time in 1 minute in order to maintain the gravity that's equivalent to Earth.